A warm welcome. This is Control Systems course with lecture 1.5 representing the block diagram reduction techniques. Block diagrams are the representations of the transfer function of a system, the input to a system, and then what and all the operations which are being performed in a system. This is what is we are going to represent in the form of block diagram, so that the calculations can be made easily. We are calculating transfer functions, we are writing differential equations, and then we may be supposed to use state space model. We have a number of techniques in order to calculate. So these calculations can be made only when the system representation is made in a possible manner. For that purpose, we are going to use the block diagram reduction technique. Here, a system that can change its output in accordance with the change in input is known as a closed loop system normally, and this can be implemented by introducing a feedback path in the open loop system. So this is how we represent a small block diagram, which is simple. R of s is the reference input, B of s is the feedback input, and then E of s is the error, which is then fed to G of s, that is the transfer function of the system or the process itself, and finally C of s is the output. From C of s, a sample is being taken and fed to the feedback element H of s. This will produce a feedback output B of s. So in this way, here we have used one summing point, two blocks, and here it is a node. From this node we have taken that value. So arrow representation is very much important in case of a block diagram reduction technique, because only with the presence of the arrow direction we can find out where the signal is going from, where from to the may be easily identified. So as I said, we have block, the summing point, and the node. There are certain rules for reducing the block diagram technique. If suppose two transfer functions are connected in series, they can be multiplied, that is, they can be cascaded. If two transfer functions are connected in parallel and they are connected in forward manner, here it is from left to right, and here is also, it is also from left to right. So that forward manner representation of summation or subtraction, whatever it is, we can manipulate them or we can reduce them into one as either addition or subtraction. Next, by moving the summing point behind the block, so from this point, from this point to this point, we are moving ahead. Yeah, we are, suppose if we are moving this point to this point or this, so that moving ahead is or behind, here it is mistakenly given, I'm sorry, this is moving a summing point ahead of the block. So we are moving this summing point ahead of this block. When it is moved ahead, for example, here the input is x, here it is y, here it is g, and here we are getting an output as z. So the main path has to be considered here. We have shifted the summing point here. Here it is x, it is g, the summing point, and it is z. So what we have to do is we are going to insert this feedback element to the summing point. So while you are inserting, we have to multiply with g, because this is said, when you consider normally what is the value, here it is x plus or minus y, let us consider this as plus, x plus y into g. So what is the answer here? It is xg plus yg. Hence the same representation should be here, the z value should be the same. Here we have x value, it will be multiplied to g, so here we will have xg, and what we need here to represent the value of z as xg plus yg, we are in need of yg. Here it is already the multiplication, so we are getting xg plus yg directly. Here we have only xg here, so what we have to do is we have to give this y value to a g, and so finally forming yg. The xg and the yg will be getting added here, and we will get the z value. So simply, while moving a summing point ahead of the block, you have to multiply the branch with g. So the second opposite term, if you are moving the summing point behind the block, then you have to multiply with 1 by g. While you are considering the branch point, when you are moving the branch point ahead of the block, then automatically you have to multiply with 1 by g, and if you are moving the branch point behind the block, then you will be considering the multiplication of g in the branch. And while suppose you are eliminating the feedback loop, here in the second rule we have seen feed forward terms because both the lines are in forward term. While you are considering a feedback term, then you have to reduce it accordingly. The value is g is a transfer function and h is a feedback element. If suppose it is a negative feedback, I mean here it is positive, here it is negative. If it is a negative feedback, then the reduction value will be g divided by 1 plus gh. If it is a positive feedback, that is both plus term in the comparator, then you will have g divided by 1 minus gh. And if we suppose interchange the summing point, then obviously if suppose it is w and x here, and here we are getting the value of w and plus or minus x with along with y. If you are interchanging, then it is w and y with a combination of x. Obviously we'll be getting the z value to be the same. It is g1 g2 and h1, and it is a negative feedback. We are having g1 g2 divided by 1 plus g1 g2 into h1, and here we have shifted this branch point to the ahead of the block. So we have a h2 divided by g5 here. Here this is another feedback loop, and so here we have a cascaded element. So g3 plus g4 into g5. We can reduce this feedback path. We have an equation. These are connected in cascade, so it can be multiplied, and again it is a positive feedback loop. We can apply this accordingly, and then we can find out the transfer function y of s by r of s. It's a simple calculation.